Professor for the kind introduction. Good morning, everyone. I am Sudarsan Majumder from Indian Institute of Technology, Madras, and my talk is entitled "A Direct Piezoresistive Method to Transduce Electromechanical Motion in Self-Sensing Suspended Nanostructure." The paper is about. So the talk is about the vibrations induced in nanostructures, and during the course of my presentation, I will be briefly going through the following outline. And I will start with the introduction to nanoelectromechanical systems. Then I will lay the motivation as to why we chose this particular project. And then I will talk about the fabrication of a test device on which we validated our model. I will talk about the development of the analytical model of the proposed transduction method. And then I will validate this model with a comparison with experimental results before I finally conclude my talk. So to start, basically with scaling of device dimensions, the resonance frequency or the sensitivity of resonators increases because we go on increasing the surface to volume ratio, which induces more surface phenomena compared to the bulk phenomena. And also with miniaturization of devices, the effective mass of the resonating of the vibrating structure also decreases, which causes the sensitivity of the resonance frequency to mass loading effects to increase. And therefore, nanoelectromechanical systems are one of the most highest class of sensitive devices out there. But in order to integrate these devices in real-life applications, we need on-chip implementation. And on-chip implementation requires all electrical actuation and readout. The problem with electrical readout is that the detection or the sensing of such minuscule nanoscale motion in the background of high-frequency parasitic noises is extremely difficult. So people have come up with few techniques. The most popular among them is the capacitive method. And the capacitive transduction method basically utilizes the variation in the capacitance between the vibrating structure and the gate electrode induced by the mechanical motions to transduce the mechanical vibrations. But this method is very restrictive in nature because it gained traction with the emergence of graphene mechanical systems where the transconductance is very high. So this method uses that high transconductance to amplify the signal. And for most materials, you do not get such high conductance. So therefore, this method is not so suited for all materials in existence. And secondly, if you see the resonance line shapes for different increasing drive voltages, you see that the baseline value or the background current also increases because of the increase of drive voltages, and this limits the detection range. And thirdly, to maintain power or to get an efficient power control at the drain and the gate, you actually have to implement a very a complex circuit which increases the size of the circuit and it makes it bulky. And finally, capacitance switch measurement depends on the area of the device. And as you shrink down on area, for example, in nanowires or nanotubes, you get very low capacitances. And the variation of such minuscule capacitance is extremely challenging to detect in the background of the noise. So in this research, we are proposing a piezoresistive transduction method where its very simple circuitry has been implemented. And this method does not depend on the transconductors, and therefore it can cater to a wide range of materials. We will see as we go on later on slides that it also has a non-scaling electrical background as opposed to a capacitive method with scaling background. And overall, it's a better method for low-dimensional nanosystems because it does not depend on the area. It depends on the actual strain experience of the device. So to start off, I will first explain the fabrication of the resonator. And we first take a thermally oxidized high-level silicon substrate on top of which we spin coat graphene oxide to get a continuous layer. And then we chemically reduce this graphene oxide to reduced graphene oxide or RGO. And then we pattern this RGO using photolithography and reactive ion etching, and then we coat metal on top of it, and then pattern the metal using photolithography and lift off. And then we do a localized wet etching of the membrane to release the membrane in buffered oxide etching before we finally dry the sample in supercritical carbon dioxide. So here you can see the actual image, the high resolution scanning electromicrograph of the structure beside the schematic of the device. And roughly the device dimensions are about 5 micron in length, 3 micron in width, and the thickness of the membrane is about 4 nanometer, which has been confirmed using AFM. And the depth of the trench dug underneath the membrane in the SiO2 is 285 nanometers. So let's come to the analytical model. We actuate the membrane by first applying a DC voltage, which causes an equilibrium deflection of the membrane, and then the superimposition of a small signal AC voltage at frequency F on top of the DC causes the membrane to oscillate at the frequency F above the asymmetric equilibrium position, as shown in this schematic over here. And how we model that actuation is we express using multivariable first order Taylor series expansion the conductance or the modulation of conductance as a function of modulation of charge and modulation of strain, because these are the two parameters that actually modulate as the membrane vibrates. And because the vibrations are extremely small compared to the lateral device dimensions, we can safely take a parabolic deflection approximation, which allows us to calculate or estimate the modulation and strain of the membrane by doing some geometrical analysis. And combining all these equations together and then expanding, we get a form of the modulated conductance, which is the combination of different time-varying spectral frequency components, which are mutually commensurate in nature. That is, they are at DC, F, twice F, and so on, as shown by the different colors. Now, the interesting thing is the information of mechanical motion or the information of the signature of resonance is present in each of these components implicit within this delta Z term. And this delta Z is the amplitude of motion of the vibrational amplitude. And transduction of any one of these components can give you the information of mechanical resonance or electromechanical motion, as you say. But in order to keep our circuit extremely simple, we choose and target that component that does not have a time varying nature. That is the one component that sits at DC, and it's exactly this component which has been shown in red. And the way we do it is we drive a very small current through the membrane, sourcing it at a small voltage VD, which is at a low frequency F delta, and we use that low frequency to clock the lock-in amplifier over here. And because of the heterodyne mixing happening because of the membrane vibration, at the output you get current components at F delta and F delta shifted F delta shifted to ISF, all the side bands. Now, since the lock-in amplifier is referenced at F delta, it only monitors the component at F delta and rejects all other components. And therefore, the only component that the lock-in amplifier allows to pass through is this component, and it processes that signal and gives an RMS value in the form of this. So basically, this is the development of the model of our transduction method. And to validate the model, we have characterized our fabricated device in the same circuit configuration as shown here. And the characterization results has yielded us the following outcome. We observed 3 peaks, A, B, and C. Out of these 3 peaks, the peak A over here is actually not because of membrane vibration. It is because of a spurious electrical resonance arising from impedance mismatch in the circuit. So in the further analysis, we shall avoid this peak A and concentrate on peak B and C. If you look at the variation of the peak B and C with respect to the different increasing drive voltages, you see that the different resonance line shapes converge to the same baseline value, which is defined by this G of Vg, which is the equilibrium conductance of the membrane. And therefore, we say that our method does not have a scaling background; it has a constant background, and therefore our range is not restricted over here as the capacitive method. Now, in order to test whether this lock-in the lock-in current is actually varying a square of the displacement or have a quadratic dependence with the amplitude of motion, we plot the peak lock-in current with respect to the AC gate amplitudes, and we see that a simple quadratic fit exactly describes the nature of variation of the lock-in current with the AC gate amplitude. Therefore, our experimental results agree very well with the model that we have developed. And one important thing about this transduction method is that since the current varies a square of the displacement, we have to be careful while measuring resonance features such as the resonance width and quality factor by fitting the Lorentzian line shapes. Here, the resonance width and quality factor will be given by the full width quarter maxima instead of the half maxima, because the current is varying its quadratic with the drive amplitude. So to come to the conclusion, we have proposed a transduction method with a which is piezoresistive in nature and which is a non-scaling electrical background, as opposed to the capacitive method, which is a scaling background. We have implemented this using a very simple circuit configuration, which allows us to play around with circuit parameters very easily. And we have developed an analytical model for this transduction method, and our experimental results agree very well with our analytical model. The simple outlook of this research is that this method can be a more holistic and universal method compared to the restrictive capacitive method, because it caters to a wide range of material and has the potential to better transduce a wide range of nanoscale geometries. So finally, I would introduce you to my thesis supervisor, Dr. Soumya, who is also the author of this paper. In the course of this work, I have had engaging discussions with many faculties in our department whose name I have acknowledged over here. I'm thankful to Center for NEMS and Nanophotonics, IIT Madras, for providing us the fabrication and characterization facilities. Here is a picture of me doing the same work in our clean room. And I'm also thankful to MEIT and BSc Government of India for providing us the financial support. Thank you for listening to our presentation.